right, we're ready to start here, the seminar, this weekly seminar. We do not have a seminar next week. Just keep in mind that spring break doesn't mean you don't have to come here and work, but there's no seminar and there's no pizza. Today, Hassan Kazmee is going to speak. He's had a bachelor's degree from Bangladesh and then a master's degree from University of Oklahoma in Norman. And he's working at Professor Tutumba's groups on granular materials. And in fact, this project I'm somewhat familiar with because this was started as a class project. Not all class projects go anywhere, but this one turned out to have some interesting work on the effects of blending recycled aggregates with virgin aggregates, and kind of actually wrote a paper on this that we haven't quite finished, but that's a different subject.
Well, there's a TRD paper on it, but there'll be more papers.
Yeah. As you know, papers are never finished. It takes a long time to finish that last 5%. So, Hassan, please let us know what's going on.
Thank you, Professor Isler. Good afternoon, everyone. Today I will be talking about the effects of material blending on strength, modulus, deformation characteristics of recycled concrete aggregates. Let's jump into the content. First, I will be giving you some backgrounds, followed by aggregate properties, then methodology, how did we do this. Then I will discuss about the results and discussion, limitations of this study, summary of this study, and finally, I will talk about some of the recent development that is going on in the recycled concrete aggregate research. So, as we are running out of good quality virgin aggregates, so we are kind of pushing towards the optimized use of recycled concrete aggregates. The scarcity of good quality materials is resulting from high construction demands, environmental concerns, as well as ever increasing oil and gas prices. So, but whenever it comes to the question of using the recycled concrete aggregates alone in our conventional design methods, we are not picking it up that way. We are blending these recycled or reclaimed aggregates with the virgin aggregates for regular design approaches. So far, the DOTs have pleasant experience with these type of conventional blending, but from literature review, we have also come to know that 50-50 blend, that means 1:1 blend of RCA and virgin aggregates tend to have lower severe, that means lower California bearing ratio, as well as inclusion of recycled concrete aggregates increases the optimum moisture content. On the other hand, RCA is proved to be promising in terms of mechanical performance, but yet there is a possibility of higher frost susceptibility in case of recycled concrete aggregates. So our objective of this study was set to evaluate the effectiveness of these material blends in terms of mechanical performances, and for that we chose 4 different material combinations, that is 100% recycled concrete aggregates, 100% virgin aggregates, 3:1 blend of recycled concrete aggregates and virgin aggregates, and 1:1 blend of recycled concrete aggregates and virgin aggregates. These are the 2 materials that we have used in this study. One was the crushed dolomite from the Vulcan Quarry, Kankakee, Illinois. I got it from the ICTR 27-81 project, and the recycled concrete aggregates were extracted from the Chicago O'Hare modernization project. If you look at the properties of these 2 aggregates, you can see that virgin aggregates have higher bulk specific gravity and lower absorption capacity compared to the recycled concrete aggregates. The Los Angeles abrasion ratio was quite similar for both of the aggregates, and both of the aggregates have non-plastic fines. So if we look at the gradation of the 4 blends, the 4 blends is generally fitting into the conventional I.CS specification limits. We have also checked out the aggregate shape indices like surface texture or the angularity with the UFI aggregate image analyzer. And in these slides, we can see the results. If we look at the results, virgin aggregates tend to have higher angularity index as well as flat and elongated ratio, higher flat and elongated ratio. But the surface texture index of both virgin aggregates and recycled concrete aggregates are quite similar. Then we came up with a test matrix. We have done the moisture density relationships with modified compactive effort, and at each compaction point, we have also done the unsoaked California bearing ratio test, which is also known as Illinois bearing value. Then we have done the resilient modulus test according to the AASHTO T307 standard specification with both horizontal and vertical pulsing. In fact, vertical pulsing followed by horizontal pulsing. Then we have developed our own protocol for multi-stage permanent deformation test, where the stress ratio, principal stress ratio, is ranging from 2 to 10. So first look at the AASHTO T307 standard. It starts with the conditioning phase of 1000 load cycle applications with a stress ratio of 2 only. Then we have 15 different stress sequences with 100 load applications, and these you can see the stresses that we are applying on the sample according to the AASHTO T307. And in general, researchers used to refer to the permanent deformation at conditioning phase is the representative behavior, representative permanent deformation behavior at that for that corresponding material, where the sigma 1 divided by sigma 3 is equal to 2 only.
Hassan, you want to clarify why it's sigma ND there in that table? Why it's not 1D or 3D for what you're noting? That's because we pulsed in the vertical and then in the horizontal.
Yes.
So it should be 1 in the vertical and
Yes.
3 in the horizontal.
Now, if we take a look at this picture, we can see the wheel is moving, as well as the principal stress axis for principal stress is also rotating, and it is inducing kind of extension, compression extension, and compression type of loading. Similar results were also found out from this project, field performance deformation results done at National Airport Pavement Test Facility, where they have failed flexible pavements with up to 4-inch rods. And from those test sections, they have come up with this type of loading sequence: extension, compression, and extension. When you have this type of moving load, fast moving load, and your granular materials often experiences directional dependency, and this directional dependency cannot be well portrayed with the conventional AASHTO T307, where you pulse your specimen only in the vertical direction, but you have also horizontal stiffening while you have horizontal stiffening, material stiffening in the horizontal direction. Tudumler and Kim also studied the effect of multi-stress path in the same project, and as we can see that in both cases they have compared the single path and multiple path test results, and both the volumetric and deviatoric strain for the multiple stress path test consistently were higher than those ones from the single path test. So moving wheel load effect is quite dominant here. So from the above discussion, we can come up with two important aspects: that rotation of principal stress. So we need a test specification that can account for the directional stiffening. Also multiple stress paths. We need also a type of test that can simulate multiple stress path. So Professor Tutumluar has done a lot of work in the anisotropic modulus, anisotropy based area, and he found that anisotropic modulus ratio have been found to be a good material quality indicator. Anisotropic modulus ratio is nothing but the ratio between the horizontal resilient modulus and the vertical resilient modulus. So we are pulsing the specimen in both vertical and horizontal direction and coming up with MRH and MRV, and from that we are correlating the directional effect of directional dependency with the material performances. And this is the equipment that we have used. Then we have developed another test protocol which is called multi-stage permanent deformation test protocol, where we have generated multiple stress paths. The test is constituted of 5 different stages, each stage constituted of 16,000 cycles, where we have very low amount of confining pressure, approximately 3 psi, and the principal stress ratio is ranging between 2 to 10. Now we will jump into the results and discussion. These are the results for the compaction characteristics. If we look at the results, we can see that with the increase in RCA, the optimum moisture content increases. On the other hand, maximum dry density decreases. If you recall the results from the specific gravity test and the absorption capacity test, you can also draw the probable cause for such behavior. The increase in the optimum moisture content is due to the higher absorption capacity, and the decrease in the maximum dry density is due to the lower specific gravity. On the other hand, you can see the effect of blending on peak severe in terms of shear strength index. You can see the single source materials like RCA and VA at higher peak compared to the blended materials like 3:1 blend or the 1:1 blend. Oh, sure. These are the resilient modulus test results. Also, if you take a look at the resilient modulus test results, the vertical and horizontal resilient modulus, you can see that the single source materials, the unisource materials like recycled concrete aggregates and the virgin aggregates outperform the blended materials. Most probably this is due to the lack of packing because of the differential angularity and flat and elongated ratio of the 2 different types of aggregates. And we have also fitted these resilient modulus to two well-known models. One is the K theta model and another one is the universal model. And if you take a look at these numbers, you can see that the single source materials like recycled concrete aggregates and virgin aggregates has higher K value compared to the 1:1 and 3:1 blend, which represents the bulk stress term. So an increase in the K value results in the increase in resilient modulus value. So the single source materials and the virgin aggregates materials had higher K values compared to the blended materials. Now comes the anisotropic modulus ratio, the MRH and MRV, and this figure tells the ratio at 3 different stress states: low stress state, intermediate stress state, and high stress state. It's generally experienced that this ratio increases with the increase in stress states for good quality materials, just like stiffening behavior, whereas poor quality materials exhibit overall decrease or not so well increasing trend in modulus ratios with an increase in the deviator stress. So if you compare the results between the four material combinations, among the four material combinations, you can see that the single source materials showed constantly increased anisotropic modulus ratio with increasing stress level, whereas the blended materials didn't show such increase. Now we'll jump to the multi-stage permanent deformation test. As we can recall that in the conditioning phase, when we are representing the permanent deformation behavior, it was the principal stress ratio was only 2. But if you look at here from the multi-stage permanent deformation test, you can see that you cannot differentiate between the three blends, like 3:1 blend, 1:1 blend, or virgin aggregates. So how do you expect to portray the exact permanent deformation behavior at such low stress ratios? So you need to come up with higher stress ratios so that the differences in permanent deformation behavior become clearly apparent. And that's what we did. And the result is like this. Sorry. The 3:1 blend of RC and VA had the highest permanent deformation. On the other hand, recycled concrete aggregates had the lowest permanent deformation. And again, if you take a look at this table, you can see that the single source materials were also performed better than the blended materials.
Was that a replicate of one specimen?
This was a one specimen replica. Now the concept of shakedown. Each permanent strain curve of a particular stress path, it is categorized as one of the three possible shakedown ranges. A is plastic shakedown, where you have stable permanent strain rate decreasing with the increasing load cycle or stabilizing like this. Then you have zone B, plastic creep, where permanent strain rate is not decreasing and appears linearly increasing. On the other hand, zone C, or the incremental collapse, is generally high permanent strain and sample fails before the end of test. In fact, zone C looks like a lot like the flow number test, where you are jumping from the secondary to tertiary stage of permanent deformation accumulation. Workmeister et al. Did a lot of work in the concept of shakedown, and she has come up with a range for these, a range for the shift from plastic shakedown to plastic creep, and then plastic creep to incremental collapse. The range between the plastic shakedown, the limit between the plastic shakedown and plastic creep, she determined it as 1 × 10⁻⁵, and for the range of incremental creep, plastic creep to incremental collapse, she determined the range as 1 × 10⁻⁴. In our cases, we have also found similar results, just like Workmeister. Typically, with an increase in the stress ratio, the specimen showed increasingly higher permanent strain accumulations, as you can see here. Similarly, the strain curves change corresponding shapes from concave downwards to concave upwards. Yet, none of the materials underwent incremental collapse represented by concave upwards curves. If you can recall the numbers that we mentioned in the previous slide, you can see that even at a stress ratio of 10, none of the materials went above 1 × 10⁻⁴ strain limit. So none of the materials underwent the incremental collapse. Here comes the limitations. We used two different types of materials, the virgin aggregates and the recycled concrete aggregates, but they had two different types of fine content, which may have affected affected the mechanical performances. This is a very material specific test results. If you can recall, the recycled concrete aggregates were extracted from O'Hare modernization project. So it is expected to be premium quality aggregates. But whereas if we are extracting the recycled concrete aggregates from somewhere else with low importance value, then the results may be different. Also, we did the test, the multi-stage permanent deformation test with 5 different stress states, but all of them were on the single specimen. So there might be an effect of a stress history effect, and only mechanical performance was judged, whereas we didn't compare the durability aspects or the frost susceptibility aspects. So these are the limitations of this study. So the summary of this study is recycled concrete aggregates exhibited consistently higher strength and modulus properties. Also, they accumulated lowest permanent deformation. The virgin crushed dolomite showed the highest degree of moisture sensitivity due to the 13% fines content when compared to the RCA with 8% fine content. Strength modulus test results indicated single source RCA or VA materials performed consistently better than the blended materials. Similarly, multi-stage permanent deformation test also showed that significantly higher accumulation of permanent strain was experienced in case of the blended materials. But this study used a controlled gradation of recycled concrete aggregates. But in reality, is it so? We are using, in reality, are we using this type of controlled materials? Maybe not. So that's why here comes the project. We are yet to start this project for the evaluation of aggregate subgrade materials used as pavement subgrade and granular subbase. The objective of this study is said to develop an characterization technique of aggregate subgrade materials in terms of source, composition, particle size and shape properties, then evaluate field performances of the most commonly utilized aggregate subgrade materials for unsurfaced working platform application and asphalt surfaced low volume pavements. And finally, revise and develop material specifications governing the use of these materials in pavement applications. So the tasks are like establishing types and compositions of aggregate subgrade materials in Illinois, developing a methodology to characterize size and shape properties of selected aggregate subgrade materials, construction of field pavement test sections with selected aggregate subgrade materials. Task 4, field performance testing with accelerated pavement testing, dynamic cone penetrometer for correlation to CBR, nuclear density gauge for density, lightweight deflectometer for the modulus values. Then finally establishing field designs for selected aggregate subgrade materials for unsurfaced working platform application, and then asphalt surfaced low volume pavement application. For developing the methodology to characterize size and shape properties, we'll not go in details. As you can recall from 2 weeks earlier, Aaron's presentation, Aaron presented something similar. What we are doing here, we are spreading the aggregates on this green background, Disney color, and we are spreading in these aggregates in such a way so that the aggregates are not touching each other. Then from this image, we are coming up with a high contrast image where you can, based on the differences in the contrast, you are dividing the pictures into different regions. And from those different contrast regions, you can come up with a simplified black and white images. And from those black and white images, you are correlating the performance, you are correlating the size and shape with the already established University of Illinois aggregate image analyzer processing size, angularity index, and surface texture indexes. Now, for this study, we'll be actually constructing field test sections with these materials. CS6 is the CS6 and the CA2 are the conventionally used base materials, whereas CS1, CSO2 is crushed stone with 2 different gradation with large top aggregate sizes, and the RR1 is the crushed concrete aggregate, where we will also be using the crushed concrete. So in this project, we will be using crushed concrete aggregates, recycled materials, as well as RAP, recycled asphalt pavement materials. And these are the thicknesses of the corresponding test sections. These are the pictures of accelerated pavement testing with Atlas, nuclear density gauge, dynamic cone penetrometer, lightweight deflectometer. And after we have done this, some of these materials will also be tested with the large triaxial apparatus called TX24. At first, we'll be determining the shear strength of the corresponding materials in the field with this TX24 setup. Then we will find out the expected level of confinement that we'll be having in the field. And based on the level of confinement, we will determine the deviatoric stress required to reach the SSR, I mean subgrade stress ratio of 0.70. And we'll do it incrementally so that we can run a multi-stage permanent deformation test to check out the comparison between laboratory and the field performance of the permanent deformation behavior of these materials, recycled materials, as well as large stones that we are using in the field. So that's all.
Questions for Hassan?
Can you mention the typical sizes of subgrade active materials or
Oh,
otherwise
the top size is 6
more
inch,
granular materials?
6 inch, 8 to 6 inch,
From 3 inches to 9 inches or
3 inch to 9 inch.
but most will be around up to 3 inches, especially crushed concrete cases.
You said that the fines content affected the results.
Yes, it might.
In what way would different fines content there? I mean, is it a possibility, or do you think it actually made the results the way they were? You get my question? You said, do you think it had an effect in separating the results, or is that just a possibility?
That's a possibility. I'm not sure.
I also had a question about the horizontal modulus versus the
Yes,
vertical.
sure.
For other materials you've tested, I mean, what's the magnitude? I mean, is that in line with other materials?
Yes, definitely. Generally, you expect the anisotropic modulus ratio to be from 0.4 to 1, and it will increase with the stress ratio when you have higher stress states. So if we look at the results here,
It's something like 0.5 to 0.65.
yes,
But for other materials in Illinois, would that be typical, or are we
yes,
dealing
that's
with a better
quite
material?
typical. Yeah,
So this would be normal.
yes. But it should have an increasing trend,
Sure.
not like this.
Anyone else? No one has a question. How about if we threw RAP in there? What would happen?
Permanent deformation will be high, very high.
So you don't recommend that?
well, permanent deformation will be high.
How about the modulus?
Modulus will also be high.
Yeah. Because that seems like a possibility, is to use RAP as a subbase. People have done that. I'm just curious how it would, my guess is I would agree with what you said.
And they have, several studies have found that in the field, permanent deformation actually accumulates a lot when you have RAP. But if you just test in the lab for modulus, you actually get a very good indication that it's a very strong material. So it's probably the, I don't want to term it wrong, but viscoelastic or some kind of behavior of the asphalt coating and stuff like that.
So it has some type of creep effect
Yes.
over time?
Yes, for deformation. We actually did some testing for Professor Jihan over at Kansas. And his student, he had actually also brought some RAP, and we did it with Passer, and we found exactly same. Modulus values were very high, even higher than virgin materials, but when you go to permanent deformation, they were like twice as much or something. So yeah, it was very interesting.
Okay, well, your colleagues are being soft on you. Thank you.
Thank you.
Thank you, Dave.